I am going to show you a rule that a 10-year-old can follow, and that has broken every mathematician who has ever touched it. Here it is. Take any positive integer. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Then repeat. That is the whole game. So let's play. Start with 27. 27 is odd, so 3 times 27 plus 1 is 82. 82 is even, so divide by 2, 41. 41 is odd, so 124. Divide, we are at 31. Keep going. The numbers climb, they crash, they climb again, and eventually, after exactly 111 steps, you land on 1. But 111 is not the part that will ruin your day. The part that will ruin your day is the number this thing peaked at along the way. 9,232. From a starting value of 27, that is the peak the sequence reached before coming back down. Plot the whole journey with step count on the horizontal axis and value on the vertical, and you get something that looks nothing like arithmetic. It looks like weather, peaks, valleys, a violent bounce off the ceiling, then a long slide down to 1. Mathematicians call these hailstones because the values go up and down like ice crystals in a storm cloud before finally hitting the ground. That is what 27 does. Pick any other starting value you like, and you get a different hailstone, a different shape, a different peak, a different length. And here is the thing, in every single case anyone has ever checked, the hailstone eventually hits 1, every time, without exception. So the obvious question is, does it always? For every positive integer? That question is the Collatz conjecture. Stated precisely, it says, for every positive integer you start with, iterating the rule eventually reaches 1. That is it. That is the entire conjecture, and it has been unsolved since 1937. Jeffrey Lagarius, a number theorist at Michigan who has studied this thing for decades, calls it a really dangerous problem. He says, people become obsessed with it, and it really is impossible. Paul Erdos, who won 2 Wolf Prizes and published more papers than anyone alive, said about this problem, mathematics may not be ready for such problems. Erdos, who was ready for almost everything, said we were not ready for this, so let's see how far we have pushed it. The simplest thing you can do with an unsolved conjecture is hand it to a computer, and for the Collatz conjecture, people have been doing exactly that hard for 60 years. The current record comes from a 2025 effort on LUMI, one of the most powerful supercomputers in Europe. They verified the conjecture for every positive integer from 1, all the way up to 2, to the 71st power. Let me tell you how big that is. 2.36 sextillion, a 2 followed by 21 zeros. Every one of those integers checked. Every one of them reaches 1. That is the weight of evidence sitting on one side of the scale, a number so large we do not have a common name for it. And on the other side of the scale, sitting there smug, is the fact that this still is not a proof, because there are infinitely many integers, and there is exactly one you might have missed. Okay, so why does this thing seem to always come back to 1? Here is the intuition, and it is a beautiful one. Pretend for a second that Collatz is random. It is not random, but pretend. Take an odd number, apply the rule, you get 3n plus 1, that is always even. Now ask, how many times, on average, can you divide by 2 before hitting another odd number? Half the time you divide by 2 once, a quarter of the time by 2 twice, an eighth of the time 3 times, and so on. The expected number of halvings is 1/2 plus 2 times 1/4 plus 3 times 1/8, which sums to 2. So on average, 1 odd step multiplies by 3, and 2 even steps divide by 4. Net factor, 3/4. 3/4 is less than 1. So on average, every odd number shrinks by a factor of 3/4 each round. Orbits want to decay. If the process were truly random, this argument would be a proof. Starting values would shrink geometrically, and everybody would hit 1 eventually. But it is not random. It is deterministic. And that difference is the reason we have been stuck for 90 years. On average is not a theorem. The word on the street, if mathematics has a street, is that Collatz is hard because it has no algebraic structure. What does that mean? Most problems in number theory give you something to hold on to. A modular relation, a generating function, a prime factorization that behaves. Collatz gives you none of those. Watch what happens to the binary representation of a number under the rule. 27 in binary is 11011. Multiply by 3, add 1, you get 101010. That is 82, and the bits have completely scrambled. Do it again, and there is no pattern in the bits. Every standard tool in the number theorist's kit depends on pattern. Collatz burns the kit. It gets worse. In 1972, John Conway proved that a slight generalization of the Collatz rule is Turing-complete. Translation: there is a version of this problem that is mathematically equivalent to the halting problem. If you could solve that version, you could solve every decidable question in computer science. That is what sits behind the innocent 3n plus 1. So where does this leave us? For 70 years, essentially nothing moved. Then, in 2019, Terence Tao, who is probably the best living mathematician, put a preprint on the archive. The title was, "Almost all Collatz orbits attain almost bounded values." Let me translate the title, because every word matters. Almost all. Tao proved that the set of integers for which the conjecture works is, in a precise technical sense, almost the entire set of positive integers. Not all, almost all, attain almost bounded values. He did not prove every orbit reaches 1. He proved that almost every orbit eventually visits a value much smaller than its starting point. You can make much smaller mean whatever you like. The minimum of the orbit can be less than log n. Less than the logarithm of the logarithm of the logarithm. If you understand how weak that is, you also understand how strong it is. He showed that, for a near 100% fraction of starting values, the Collatz map eventually crashes the value way down. It was and remains the biggest result on this problem in half a century, but it is not a proof. Tao himself said this. You can get as close as you want to the Collatz conjecture, but it is still out of reach. He got the 99% answer. The 100% answer is exactly as far away today as it was in 1937. So here is where we are. We have a rule that a 10-year-old can follow. We have 2.36 sextillion confirmed examples. We have a probabilistic argument saying the orbits should decay. We have Conway telling us a slight generalization is undecidable. And we have Tao telling us almost every integer almost satisfies the conjecture. And it is still unsolved. This is the strangest kind of mathematical problem. The statement is so simple you can teach it to a child in 30 seconds. The answer is so hard it has defeated every mathematician in a century of trying. There is something humbling about that. A century of rigorous thinking, of analytic tools, of topological tools, of computer search, and we cannot tell you whether a rule you learned in 90 seconds is true for every integer. So here is what I want you to do. Next time you are bored, pick a number, any number, run the rule. Watch the hailstone bounce around and finally land on one, and know that you are doing something nobody on earth can prove is guaranteed to happen. You will reach one, probably.